and input power boundary. I'm Scott Arnold, Senior Manager of Publications and Standards for Air Movement and Control Association International. On behalf of our more than 400 members worldwide, I want to thank you for joining us. We realize there's a lot to see and do at the AHR Expo. We respect and value your time and hope you find this educational session well worth your while. The information contained in this session is provided by AMCA as an educational service. In making this educational activity available, AMCA is not endorsing, sponsoring, or recommending a particular company, product, or application. And lastly, this session is protected by U.S. and international copyright laws. Reproduction, distribution, display, and use of the material without written permission from AMCA International is prohibited. With that out of the way, let's meet our presenters. As Global Technical Director for AMCA International, Nazmi Mosina is responsible for driving integrity, consistency, and quality in the establishment and application of product testing and certification requirements. Additionally, she provides leadership to achieve technical objectives and operational goals and serves as an arbitrator in technical appeals related to standards and functions. She has a bachelor's degree in electrical and electronic engineering from Bangladesh University of Engineering and Technology, and a master's degree in electrical engineering from the University of Dayton. In 2020, she was named to Engineered Systems Magazine's 20 to Watch Women in HVAC list. But first, we'll be hearing from Mark Bublitz. Mark, who's Executive Vice President, Industry Affairs for New York Blower Company, is immediate past chairman and a past president of the board of directors of AMCA International. He joined New York Blower in 1994 with a diversity of experience, including automotive manufacturing, design of aircraft landing system simulations, and creation of data acquisition and computer control systems. Prior to being named Executive Vice President of Industry Affairs, he served New York Blower in a variety of engineering and information technology roles. He has a bachelor's degree in mechanical engineering from Purdue University and a Master of Business Administration degree from Indiana Wesleyan University. Mark?
Thank you, Scott. Woo! Regulations and standards and publications at 10:30 on a Wednesday. Ow! Let's go! All right, thank you, Scott. It's an honor to co-present with Nazmi, and there you can scan the learning objectives. So we will get into the weeds, and Nazmi is the perfect person to take us there. But let me just start by setting the stage. Let's take the big picture. The Fan Energy Index, FEI, is the fan metric, the measurement of energy efficiency for the U.S. Department of Energy. So it's a federal regulation. That's the number they're going to use. It's already in use in California with required standards. So that's the number, but fans are simple devices, yet complicated. So that, you take an impeller, you turn it around, and it moves mass in and out of the fan. But it's very complicated to regulate. The story I tell is, you can take a light bulb, and you can unplug it from any socket, any state of the country, move it to any other state of the country, plug it back in, turn it on, it works about the same. You can take a fan system that is perfectly configured to operate at its peak efficiency, unplug it from one system, take it across the street, do nothing to the system, plug it in, and it's a piece of junk. So how do you regulate that? You can't just commoditize the product and give it a number. So that's the background of FEI. Rad talked about it this morning. So fans don't all come in a box at Lowe's. So we have to figure out a way to take this simple concept of energy efficiency and a relatively simple concept of being able to compare different fan systems and say, well, how do you calculate the number? So that's the challenge of today. That's kind of where we're going. So this is a great figure. It's been around for a long time, and I'm just going to zip to the end here. So the Fan Energy Index is a wire-to-air metric. In other words, you start with the juice that comes in from the wall, and you end up with the power that goes out into the system. So efficiency, energy in, energy out. Energy in has to be at the mains. Energy out has to be into the system or the duct or wherever you're sending it. Well, look at all the places, the leaks that are in between. So we'll start at the beginning. Input power, okay, we can start with that. And I have to commend, I can't remember his name, I have to commend a gentleman yesterday for talking about a wide variety of power factor and problems with power that I didn't even ponder. So you got something going in the drive. If you have a drive, the drive's going to tell the motor what to do. Because of the way drives control motors, now you have a paired efficiency. So the motor manufacturers weren't real keen on separate those. So the efficiency of the motor drive system becomes a component of the calculation. The motor is going to have some losses. If you have a V-belt drive, well, that could be, there's another 3 to 5% down the hole. Bearing friction losses, you'll finally make it to the impeller, and then it can only act so efficient, and out you go into the fan system. So that sets the stage for all the things we have to at least anticipate to perform the calculation. Kind of a more linear path to get to the same result. So we start with the power in, motor and motor control. Well, 10 to 15, you have to match the rating of the, you should really match the rating of the drive to the not just the rating of the motor, but the anticipated draw so that those can run at about the same rate. You turn that thing down, that efficiency goes to, garbage. Drive losses, 3 to 5 is a typical number, but you mismatch it, you're not running the right tension, it's not tuned up. There's 10%. 3% in the bearings. If you have a 70 to 85% efficient impeller, well, there's another 10 to 15. And you might end up on the backside with some pretty low numbers on the whole system. So that's the big picture. I'm going to turn it over to Nazmi now. So fans, typically, like I said, they don't come in boxes from Lowe's. So we've kind of said, well, in general, there's 3 configurations. You can get a fan without a motor and control, which is kind of a bare shaft fan. You can add to that, so there's a way to calculate FEI for that configuration. And you basically have to guess at what the rest, well, it's an educated guess, at what the rest of the components and what their performance are so you can calculate wire to air. You can't do it without wire to air. Configuration 2, fan with a motor. And then configuration 3 is a fan with a motor and controller. So I'm going to hand it over to Nazmi to drill us down into these sections and work through the details.
Good morning, everyone. Thank you for coming. I just want to make the record clear. It takes a lot of courage to share the stage with one giant. And it takes more courage to have all the giants worldwide present here. So I know fraction of the people that are in the audience, so forgive me, and then we're going to all learn together. Okay, so as Mark mentioned, there are 3 configurations. First one is simple vanilla flavor. By the way, I love vanilla still. There's nothing wrong with it. So a vanilla flavor is just a fan without motor and control. Majority of AMCA fan manufacturer, they are standalone fan, right? So this is the common terminology at AMCA. Is there anybody here not in the manufacturing but in other business?
Any systems people?
So it is any, okay, so feel free to stop me. Sorry. No. And then fan with motor. So what happens whenever the fan is connected with the motor? You can, depending on the pole, depending on that pole determine the speed, the fan can be run at different speed. The fan manufacturer develops selection software or maybe printed catalog that may look like this. And then another one is configuration 3, when this is a fan, is a motor and control is included. We're going to look into more in the next slide. So look at the fan power. Power is what? Something goes in, something goes out, right? So output of the fan or the fan system, doesn't matter, is always delivered by the air. And how are you going to calculate it? Airflow, pressure, compressibility, and there's a 64 there's a constant there. And then I know there's some European manufacturers, so I'm just going to leave it as a constant. So output power is regardless of how the fan is configured. 1 is standalone, 2 is fan with motor, 3 is fan, motor, and drive. The output power is how much power is generated, right? The input power can be a little bit tricky. If the standalone fan, that vanilla flavor fan we talk about, doesn't have motor or control. It's only the shaft. That is the mechanical power. What does that mean? The shaft is moving, there's a torque and the speed that determines the mechanical input power in the system. And over here, the system is only the standalone vanilla flavor fan. And again, that is also function of torque and speed. We're going to go afterwards how to calculate those. Electrical input power. So we have some European manufacturer here, right? So what they do, they may have fan, motor, drive all sandwiched together one. Or they may have fan, AC motor, or different way. So US manufacturer, I know New Bloor is here, Canon are here, other manufacturer. So what they may have, they have motor, they may have regulated motor, sorry, they have fan, standalone fan with the regulated motor or unregulated motor, and they may have drive or not drive. So in that case, you can have electrical input power, and that's going to be measured on the calibrated motor, and that will be function of voltage, current, power factor, and others. So we are so far so good. So now let's go back to the whole system, right? We talk about the driven fan. What is driven fan? Fan is driven by the component we mentioned, right? Motor control and the drive. So drive, sometimes it's been, whenever we hear drive, we think about the variable speed control, right? VFD. But if you look at ANCA standard, usually it meant fan, motor, VFD, transmission. That whole thing we call drive. Okay, but sometimes loosely we said it like drive means the VFD only, and that transmission is that what is connected with the fan before we go to the motor. Okay, so let's talk a little bit more about the transmission. What are the transmission can be? It can be V out. What is the percentage of the efficiency? Like around 98% or so. And there's a formula. Right? So there's a formula. It goes, if it is a low power output, it depends on the input of the fan. Power, again, power input we mentioned before, mechanical power. V-built transmission is actually function of HI. I mean, we're going to go there. It's the input of the shaft input power. That's the V-built transmission loss depend on. Synchronous belt, that has got three sections. If it is smaller than something like lower horsepower, shaft input horsepower, the number is around 94%. And if it is in between, like below 5 or something, then there's a number. And then above 6 is 95%. If you don't believe me, open 207. And if you don't have 207, contact ANCA. We're going to provide you this. And then flexible coupling drive is the 98%. Okay? So far so good? Direct drive power. So direct drive means connected. No loss. The world is going towards that. How wonderful it is, right? World is getting crazy to how we can minimize the power. Except some people. They don't even care about power loss. Anyway, and the no power transmission, that means nothing. Like, direct connect, nothing. So whenever I mention direct drive may have coupling, maybe drive, and that's Mark is gonna point out a little bit later about the different arrangement 8, that may have direct drive, they may have a little bit loss. And no power means there's no loss whatsoever. Okay. I'm very visual, the people who knows me, I need to see it. So this is for me, okay? And when I talk, I work for ANCA lab technician, I told everybody, put this embedded in your phone. Okay, so electrical power come in, controller, VFD, VSD, however you want to call it, then you go to motor, then you go to transmission loss. I didn't make it up by the way, it's in after 2 seconds. Okay, so this is truth. And then this is drive, and this is the fan, vanilla flavor fan, standalone fan. Okay? So this is the whole thing called driven fan. And AMCA 210, this section is called drive. And there you go, the output. Can you guys see it? Wherever there is a mechanical, it's H. Wherever there is electric, it's W. I believe IC is the same, right? Yeah. So AMCA and ISO standard are harmonized. We are cousins or brothers. Anyway, so the people who doesn't like, so for them, there are some people who prefer the table. So there are 6 Ks. Memorize it. I'm going to ask questions. If you don't get it, I say, what is case 1? No, we're going to go to that. Okay. So case 1 is again from AMCA 210. I didn't make it up. Case 1 is you have control, you have everything. motor control, motor, transmission, and this is called boundary. Aren't you mentioning something like boundary is a not cool word or something to make it? Yeah.
All engineers know.
Yeah. We all. Boundary condition. Yes, I even like it better. So boundary condition is motor and motor control. And then, as I mentioned before, wherever you see W is the electrical input power. How do you know it? Watt, right? W makes sense. Shouldn't it be then BHP? Anyway, so C is the represent control, M is the motor, T is the transmission, I is the input. So if you have motor, controller, motor, transmission, then you get WCMTI. Okay? How simple is this? Case 2, there is no controller. So fan manufacturer may not sell their fan with controller, but they sell their fan with the motor. Then you have main and motor, that's the boundary. And that is WMTI. Okay? You guys are writing a standard now. That's what we do for living. Case 3, we have motor, we don't have transmission. That means what? Direct drive, right? That is WMI, that's less loss. Okay? And then you can have motor, control, no transmission, that's CMA. It's pretty straightforward. Then the rest is vanilla flavored fan can have shaft or no shaft. Okay. If only one thing you get out of this presentation today, make sure you understand it. If you don't let me go unless you guys get it. Okay, so we go back to the original one. We talk about configuration 1. What do they have? Fan and transmission. And how do we measure it? Shaft test. AMCA 210 and ISO 52. Thanks God I put ISO. Other than that, some European people are going to be all over me. Shaft test. ANSI and AMCA and ISO. The same. So there's a we call shaft test, that's our dyno test, that give you how to measure shaft input power. Okay? Do you want to talk about what is the
I'll jump in here.
dynamic sensor?
Well, so because Nazmi's such a graphic person, let's put some pictures in here. So once again, H is shaft power. So you can see for arrangement 1, and for those fan folks, you better know these arrangements. So H, so would be at the input of the shaft. So for arrangement 1, you usually have a belt drive. You can even have a freestanding pedestal, but typically 2 bearings, a shaft, and then there'll be a drive system connected on the opposite side of the shaft. Arrangement 4, the impeller is directly connected to the motor. So sometimes you need extended shafts, sometimes not. For larger applications, we talked about inlet boxes yesterday. So arrangement 4, okay, motor's directly connected. You see there's no shaft, no bearing between, other than the motor shaft, between the motor and the impeller. And then arrangement A, typically the motor's on a standoff pedestal. There's a shaft with a set of bearings, and there's a coupling that will sit between the motor and the first bearing. And the pedestal can be standing or freestanding, or connected or freestanding. So just another visual idea of where all the losses get peeled off. They get accommodated. It was a negotiating tactic when we were going, well, it wasn't a tactic. When we were working with the DOE to develop these standards, we couldn't just ignore pieces, or we couldn't skip any pieces, because we needed to have the best estimate of efficiency. So they had to all be thrown in. So for belt drive system, this is kind of all the places that get peeled off. And kind of the depressing part is you start at 100 and just, multiplication by numbers less than 1 are cumulative. So you end up at something, even low as less than 50% just by what that would be a legacy fan of 10 or 15 years ago. Typical application, plenum fan, direct drive. So there's no belt system, but you still have to take the drive system efficiency times the motor efficiency, and you end up and at the fan, so once again, 60-70% would be a really good system efficiency. So I'm going to flip it back to Nazmi, who's very experienced with testing things.
So we talked about this is the number, right? And now it's how do you get the number? Okay. So you go to the lab, or you have your fan with the shaft. Before we do any kind of instrument, I always focus on that what is the accuracy, what we are measuring. That is very important. What's the number get already? So I personally prefer to add accuracy at the beginning, right? So the torque meter, and this is all from 1 to 10, and the 50 to 1 is the same thing. So torque meter have accuracy 2% really. That means, and then the fan is hooked in the dyno test, right? The shaft goes out, then you're gonna start running the fan. And at our lab, we run it for 5-10 minutes to warm up the motor and the fan to come to the stable, right? So then you set the desired operating condition. The speed is the main thing. If for example 1760 or if you have a VFD, okay, different speed, you come with that speed and then you run the fan to get to the point. Then they run it for as I mentioned before, the 10 to 15 minutes or maybe 5 to 10 minutes to make it stable condition, to make sure that everything is stable. Okay. Then you measure the torque and rotational speed simultaneously from the sensor. We used thermostat for whenever you do the calibration, but then you have a handheld device speed, you can do it, but you can use your, maybe you have some DAC system that automatically calculate the speed, and then measure the torque with some tear, and then the mechanical power you measure, right? And that give you calculated fan power. This is mechanical power because we are generating the torque. It's not electrical power, it's a dyno test, okay, as I mentioned before. So how about if the fan is not tested with regulated mode, then what do we do? This part we talk about just right now is a shaft test, is AMCA 210, 50 to 1. Transmission loss come from AMCA 207. Remember I have all the different transmission, V-belt, coupling and others. That is AMCA 207 transmission. And the motor and VFD, there's a wire to shaft test. There's a PDS, power drive test system. And there are a couple ways to calculate PDS testing. You can just directly calculate input and output. You can get the efficiency. You can do that way. Or you can do some calculation method. AMCA has developed AMCA 207 and ISO also adopt that, our AMCA 207. And then 28 Red mentioned about FEI. So that also give you some calculation of default motor or motor control efficiency. So you have the shaft testing. You know the transmission comes from AMCA 207. And then about the motor, if it's a regulated motor, you take the regulated number. If it's not regulated, you have to go through the PDS testing. So now you can ask me, how do you do the PDS testing? There are a couple ways to do it. ASHRAE 222 standard actually tell you how to calculate or do the testing for power drive system. There's a Canadian standard. I'm not very familiar of, so don't ask me any question on that. It is I don't know. And I know a little bit, very little bit of this. Okay, so I know this because I was part of the TC. Wire to air is everything is built in. You just main come in and go out. Okay, it could be transmission, not transmission, doesn't matter. And AMCA standard and ISO standard both tell you how to do wire to air. Okay, so is it possible to test each and every fan? It is possible. Is it practical? No. You just can go all of these, right? So there you have to be practical, right? So that's why AMCA came up with some kind of rating method. AMCA has a certified rating program that help fan manufacturer how to calculate. So if the aerodynamically similar fan, you test smaller size, minimum speed, you can calculate how. Definitely, if you test all of the different speed, you get better number, right? But it's not practical. You have to make it easy to do it. So, and then how you can do it? So you do the test minimum speed, and you can find loss up. Fan loss is proportional, pressure is square, power is cube. You do that. That can give you rating. You can do that way. And then you can also do that the minimum diameter fan. For example, 15-inch fan you test. You can rate 18, 21, 27 from there. So usually a common practice is that one range 3 or 4 sizes usually is pretty common. Axial is different, but centrifugal is, that is the usual common way to rate the fan. Okay? And then you see that what is the range of application depending on what you like. So as I mentioned, that then you come up with the calculation you have flow, it's all fan loss, and fan loss is there forever. So, and then another thing you can do is just low speed and just high speed, and you interpolate between these two speeds. Okay? So how do you do it? This is the axial fan. So axial fan, you have the low speed. By the way, everything is from AMCA standard. This is from AMCA 211. I did not make anything up. So you can trust this. So this is the low speed, this is the high speed, and the blade pitch is there, and then you can calculate the interpolated this number. So we have a CFD expert here. Jeff, whenever you guys do the CFD and then calculation method, is it like are they you can predict from your CFD?
Yes, it does become complicated because what you put into the CFD typically comes from 3D CAD models and doesn't include manufacturing tolerances.
Okay.
Also, what you model in CFD is a somewhat idealized system. It doesn't count the guy that overpressurized it and now results in the chamber leaking. So there are practical realities that make it difficult to get a perfect match. But with some effort, we can get the real tolerances. Not first time, maybe on the third attempt.
Thank you for
But we
sharing
can
that.
get
At least you can have some baseline, right? Is it fair to
yes,
say?
and you know that's something that anyone's done. I'll send you a copy once I've got it, but there's 25 pages of that.
Oh, good.
You can get after the review. I'll send you a copy which shows how I've done it for a range of fans for somebody else. And it involves when you're taking contracts against CFD, you have to do the validation copy.
Oh, good.
Not like an engineering perspective, you always have to do the copy. From a commercial perspective, you have to do it well enough that you actually get the invoice paid.
Good, good. So the same thing for wire-to-air test, that, as I mentioned before, fan, motor control all combined together. You have input and output. So you can also, AMCA 211 tell you how to calculate between two tested speed and then range of application and then power. So there are some compressibility coefficients or some other stuff, okay? So you can take that to you. So as we start from testing, AMCA 210, all we talk about testing, and then it's also ISO the same. They fan manufacturer may be sell their fan with or without motor. They may sell with the three-phase regulated or non-regulated motor, or ECM, or any kind of combination. AMCA 210 or ISO 58.1 has a one-stop shop. But it's not practical to test at every speed. That's why we have, or every size. That's why we have AMCA 211. And this section is from shaft input power. This section. This is for wire to air. You do test 210, input and output. Then you do the rating between 211. 211 is the AMCA certified rating program for fans. I should say air movement product. And then AMCA 28 tell you that how to calculate default motor calculation. And 207 is the part load, because it's not all the time fan run at full speed in the system. So for the application, they have AMCA 207 and the different standard for the how to test PADS. So these are all covered in 2.8, and this section is for 2.11.
Thanks, Nazmi. All right, so wrapping up, we talked back to this to begin and end with this awesome figure. We talked about all of the three configurations, the three ways to compute these numbers without exposing you to the nasty innards of 207, 208, 210, 211, and 214 if you really wanted some deep reading and some heavy coffee material to dive into those standards. And it's a little, moaning a little bit as a manufacturer, we get the burden to kind of share the burden of this is what it takes to calculate these numbers. Fans are simple devices that require complex calculations to estimate their performance in real life. But if you're not in the fan manufacturing industry and you're a recipient of this information, I think it might be valuable to understand just the level of complexity at how nasty this can get. Nazmi showed configuration 2. It's like as soon as you pick a motor to be paired with a fan, there's only the fan has a huge operating envelope. The motor matched with that fan will only operate acceptably in a small portion of that performance envelope. So now if you have 5 motors that work with this fan, you've got to create a performance envelope for that, and that becomes a pairing which then gets offered to the market. If you only sell the motor, if you only configure the motor in the fan, you have to take the estimates for the drive components to present to the market. And DOE is not going to let you optimistically select optimistic performance. You'll be stuck with the low end. So the debate or the issue with the manufacturer and the market is the manufacturer clearly wants to give you the best estimate of the highest performance capability of a solution. The challenge is they might have to test literally hundreds of thousands of combinations to get that done. So over the years, my guess is as we test these, the exact combination of fan, motor, drive system, and drive will probably become available to you over time because we will just continue to test and test and test. And that's maybe a benefit, maybe a burden. That's what's going to come out of this regulation. So with that, any questions or thoughts from the audience? Yes, sir.
So early on in the presentation, you showed those 3 main configurations, including the ones where the fan would not have a motor attached to it and no source of power whatsoever. Are there any actual real practical applications of those in industry?
Well, I'll take that.
Yeah, sure.
Yes. New York Blower, we're in the industrial space. Typically, a customer comes in and says, here's flow pressure density, pick a fan. And the fan selection software will spit you out a nice selection of solutions with the FEI values. But it also has an FEI number in the selection grid so that you can make a decision based. All the other components of that drive system are estimated. So the fan efficiency at the shaft, we know a lot about that. But the further you get away from the shaft, well, we don't know a lot about that. And in the industrial market, typically you buy the fan, you might get the motor from the manufacturer, and frequently the rest of the components are integrated in the field by maybe the electrical specification has the drive system and the mechanical specification has the fan system in it. So I think that's kind of how that configuration would flow out in real life.
Okay.
Yes, sir.
A blower manufacturer just selling a fan goes to OEM air hammer guys going to put on motor and stuff, whatever it is. The BHP data is actually the shaft horsepower, and then the FEI assumes those other.
Correct. Correct. Now, to the extent that the manufacturer chooses to couple, okay, one more thing. So the manufacturer is then burdened with taking the lowest efficiency, basically the lowest thing on the market that the regulators decided to find. That becomes the max you can select for that component. So you're stuck with the lowest performing motor. You're stuck with the lowest performing drive motor combination, and you have to put a belt drive in it because you don't know the drive system if you just buy the bare fan. So the manufacturer has an incentive to start, well, I'm going to pair those two together. I'm going to put the drive system on. I'm going to stick it in the lab. I'm going to test it. Because my FEI value, the challenge for us is if that estimated combination is less than 1, you cannot sell that product in California. You can't ship it in there, right? So it's like, ooh, well, maybe if I pair that with these components, I stick it in the lab and I test it and I have a test set and I register it, and I can now sell that product combination in California. So that's the real life of where we're at.
Yeah. Can I add?
Absolutely.
So I work for MCA. I bleed MCA. So I'm gonna say that's the reason you have to, whenever you get a product or a project, make sure it's MCA certified. So you mentioned about the standalone fan, and then we don't know about motor VFD, and MCA is called default motor combination. That's what Mark was explaining. Okay. So and then whenever California treaty, what are they doing? All the fan manufacturers, if they have to sell the fan in California, they shall be, but they have to do it, upload all the information to the California MAPS database, right? And you will see there how it's calculated, so default motor business.
It looks like the default data is pretty ugly, based on the slides. I don't know.
It's not optimal. There's a significant difference between what you can configure versus what you have to take if you don't know.
But even uglier is the fine.
Yeah, that's true. Fines are bad.
Yeah. So
They're
the fine
punitive.
is- Yeah, so fine is, enforcement is really, really painful. So that's why fan manufacturers kind of like, they don't have a
The
choice.
difference between paying for the parking
Yeah,
or
or
the parking
yeah,
ticket,
yeah.
right?
No, let's just take the car. Well, thank you very much for your time and attention. We're available, but have a great day. We'll see you soon.